So these four methods of controlling field flux in a DC motor are illustrated as follows. So we are going to have four diagrams. One involving paralleling of field coils, another one tapped field coils, another one use of a diverter across the field circuit, another one use of armature diverter. So the four circuits are as shown below. Now, this is the circuit that we can use when we would like to parallel field coils. By doing so, we are trying to reduce the flux per pole. We are trying to reduce phi. Now, before the whole armature current was passing through the four field coils when they were put in series. But now, we have now paralleled, we have taken two coils, put in parallel with another two coils. This happens with a 4-pole DC series motor because we have got four coils, meaning it is a 4-pole DC series motor. Now, the current that now goes through the field coil is now a half of the original value. And by reduction of the current that moves through the field coils, we are also reducing the field flux. And when we reduce the field flux, we are bound to increase the speed of that particular motor. Now, in analysis now, we say, how would we calculate? Because there is EB2 coming in place here, and IA2 can be found from what we call torque equation. Torque equation will help us if we know the nature of the load. If we know whether the load torque is varying or constant, we can be able to evaluate IA2 from the torque equation. Now, whatever we have here, when we need to evaluate EB2, for example, EB2 will be given by a drop across the armature, which will be given by a drop across the armature plus EB2 plus the drop across the coil should give us the input voltage. So this will be equal to V minus drop across the armature, which is IA2 RA, minus a drop across the field coil, which will be IA2 all over 2 multiplying the value of the field coils. The field coils, if originally it was RS, but now it is now halved, so it will be RS all over what? 2. The original value of the field coil resistance was RS, and now because you halved, we'll get that. So this will be equal to now V minus IA is common, so we'll say IA2 is common, we take it out. Therefore, we'll be having RA plus RS, but we divide by what? By 4. So this one will give us analysis or evaluation of EB2. We are doing this because, remember, from the speed equation, you have EB2, you have EB1, you have phi 1, and you have phi 2. Phi 1 is brought about by IA1. Phi 2 is brought about by IA2 all over 2. That one should give us now the evaluation of that. IA2 all over 2 will now be proportional to phi 2. And through analysis, taking care of the constant of proportionality, this one will be directly proportional to IA2 all over 2 will be directly proportional to phi 2 before the magnetic circuit is saturated. So we go to Roman 2. Tapped field coils. Now this is the circuit for tapped field coils. By trying to move this particular terminal from here to there, we are doing reduction in the number of field coils within the circuit of the DC motor. And when you try to change what we call the resistance of those field coils or resistance of the series coil that we have, automatically you are also varying the flux varying the field flux of that particular circuit. As you vary the field flux, also the speed will also change, the speed of the DC motor. So this is the armature. This is our EB. It should be EB2. This is our V. So field diverter. Use of field diverter. The circuit for this field diverter is as shown below. Now from this circuitry, we can see very well that I D plus IS should be equal to IA2. Should be equal to IA2. Also, if you would like now to get IS, because we are mostly interested in IS, the current that flows through the series circuit when the diverter is connected across that particular field coil. That is what we are interested in, because that is what will give us what is proportional to our field flux when that connection is made. So we need to know what will be proportional to our what? Phi 2. So IS can be found by analyzing this current using the current divider rule. So when we use current divider rule, IS will be equal to RD all over RS plus RD, now multiplying IA2. So when you can be able to get IS, you will have already gotten what will be proportional to phi 2. In even evaluation of yours, as you are trying to analyze the second speed, the speed under a new torque analysis, then we can be able to know what will insert where there is IS. And by getting this, we are now through, and we can be able now, this IS will be proportional to phi 2. Then we need to evaluate EB2. EB2 will now be equal to, EB2 will be equal to the voltage, input voltage, minus a drop across the armature, which will be IA2 multiplying armature resistance, minus the drop across this series coil, the drop across that series coil, which will be given by IS multiplying RS. So IS multiplying RS. That will be the drop across these two parallel groups. And when we have our EB2 ready, and we have our IS ready, because we knew originally EB1, according to the particulars of the motor given, EB1 will be ready somewhere. Phi 1 will also be ready because phi 1 will be proportional to IA1. When EB2 is ready, IS ready, IA1 ready, EB1 ready, then from our speed equation, we can calculate what is missing from the circuitry. If it is the new speed that we need, we can be able to analyze. And this will also bring what we call an increase, because we are just trying to reduce what? We are just trying to reduce the field current that is going through what? Through our field coil. That is it. So we go to part 4. So in armature diverter, the circuit is as shown below. So when we have armature diverter, there is normally a resistance or a resistance connected across the armature terminals. And in this method, we are trying to make sure that a lot of current now flows through our field coil, the series field coil. So less current, not a lot of current, more current flows through this one. And More current, yes. So when we have more current, the flux that will be created by the series coil will now be increased. When we increase the flux, we are going to reduce the speed. So this is the only way of when you want to reduce the speed of a DC motor, it is by use of the armature diverter. Then we can be able to reduce the speed of a DC series motor. Now, from whatever we have, I2 will be equal to ID plus IA2. This implies what? If you want ID will be equal to I2 minus IA2. Now, how do you get ID? ID, as we can see, ID multiplying RD will be plus I2 RS. This one will be equal to V. That is our V. So, in case now we want ID from this expression, we can get it by ID will be equal to V minus I2 RS all over RD. Now, if we have ID, our main aim is to obtain this one plus that the drop here plus the drop here is equal to that voltage. If we have our ID, then our main aim is to obtain I2. If I2 is obtained, because that is what is flowing through the field coil by that time, then we can be able, that will stand in for phi 2. When we have something for phi 2, then we can be able to proceed and evaluate EB2. And after evaluating EB2, then we can be able, through our speed equation, we can be able to evaluate for whatever constant is missing. So EB2 will be equal to, V minus IA2 RA minus I2 RS minus I2 RS. Now, in our example one, the armature and shunt field resistances of a 500 volt shunt motor are 0.5 and 250 ohm respectively. Assuming that the magnetic circuit is unsaturated, find the resistance of the shunt field regulator to increase the speed. From 800 RPM to 1000 RPM if the current taken by the motor is maintained at 400 amps. So we note whatever we are given in our solution. In our solution, we are given V, the input voltage 500 volts. We are given RA, 0.5 ohms. We are given R shunt. R shunt as 250 ohms. We are also given I1 equal to 420 amps. We are also given I2 because it is maintained 420 amps. We are given N1 800 RPM. N2 equals to 1000 RPM. So we can draw a circuit to illustrate this so that we can be able to evaluate what we need. So from this circuitry, what we need to evaluate is the value of R that is connected in this circuit, the resistance of the shunt field regulator. This is what we call the regulator. So that's what we need to calculate from this particular circuit. So from our speed equation, we would like to know what now brings phi 1, phi 2, we have phi 1, we have phi 2, we have EB1, we have EB2. So our I shunt 1, which will be proportional, I shunt 1 will be proportional to phi 2. From this circuitry, this is now I shunt 2. This is now IA2. This is now I2. So I shunt 1 will be equal to, I shunt 1 will be equal to I1 minus I shunt 1. I1 minus I shunt 1. Just a minute. This is minus IA to IA1. This implies our IA1 will be equal to I1 minus I shunt 1. I shunt 1. So I1 is 450, but I shunt 1 will be equal to V all over R shunt, which is equals to 500 all over 250, which gives us 2 amps. Which gives us 2 amps. Now from this indication, I shunt 1 is now 2 amps, so we can now be able to get our IA1. IA1 will now be I1 minus which will be 420 minus 2, which will be equal to 418 amps. 418 18 amps. We have I shunt 2. I shunt 2 will be equal to I shunt 2 will be equal to I2 minus, it will be equal to V all over R shunt plus R, which is equals to V for 500 volts all over R shunt, which is 250 plus R. So that one will give I shunt 2. I shunt 2. With I shunt 2 ready, we can now get IA2. IA2 will now be equal to V minus IA minus I shunt 2. Not V. IA2 will be equal to I2 minus I shunt 2, which will be equal to I2 was maintained at 420 minus 500 all over 250 plus R, which simplifies to 420 into 250 plus R minus 500. This one all over 250 plus R. 250 plus R. That one will give us IA2. Now from there we can now evaluate IA2 ready, IA1 ready, I shunt 1 ready, I shunt 2 also ready. We need to get EB1 and then EB2 before we move to our speed equation. So speed equation, we need EB1. EB1 is normally V minus IA1 RA, which is equals to V. V was 500 minus our IA1 was for 18. This one multiply with 0.5. So this one gives us 500 minus 2 minus 214, which is equal to 284, 286 volts. 286 volts. EB1 is equal to 286 volts. EB2 will be equal to V minus IA2 RA, which is equals to 500 minus minus 420 into 250 plus R minus 500 all over 250 plus R. Now the whole of this multiplying 0.5. That should be equal to plus 2. All over 250 plus R. Okay. Now EB2 will be given by V minus IA2 RA2. 500 is our V. This is the expression for our IA2. Now multiplying RA, which is 0.5. This simplifies to whatever we have here. 72, 750 plus 290R all over 250 plus R. That is our EB2. EB2 ready, EB1 ready, and I shunt 2 ready, I shunt 1 also ready. So we can now proceed. We can now proceed, get the value of the unknown, which is R. But you know, and but you know, but N2 all over N1 is equals to EB2 all over EB1 multiplying phi 1 all over phi 2, which is the same as N2. This implies as N2 all over N1 will be equal to EB2 all over EB1. Now multiplying I shunt 1 all over I shunt 2. This implies 1,000 all over 800 will be equal to EB2 72 750 plus 290R all over 250 plus R. That's our EB2. We multiply it by I shunt 1, and our shunt 1 was 2 amps divided by EB1, which was 400, EB1 286. EB1 was 286. 286 times now I shunt 2, which is 500 all over 250 plus R, which simplifies to 2. So an analysis of what we had as we replace our values for N1 and 2, EB2, EB1, I shunt 1 and I shunt 2. We are calculating all this and transposing for R, and therefore R is equal to 57.33 ohms. Always that value should be a value which is less than the original field circuit resistance. That is the original shunt field resistance. It cannot be above that value because we are only trying to add some small percentage of that particular value. So R is equal to 57.33 ohms. This is the one that will make now our motor to operate at 1,000 RPM when we try now to reorganize the field circuit. That is the resistance of our shunt field regulator.